Homework solutions, static simulation, thermal analysis. Um, so we do have a problem that the objective of these exercise is to evaluate the performance of a heatsink in cooling the CPU component. And as it says, essentially a model file is provided. As you will see, there's a CPU here with a heatsinks attached on top of it. According to problem statement, they said the CPU is made out of copper and has a heat dissipation at its lower phase with total heat power of 40 watts. So essentially, this phase is going to dissipate heat of 40 watts. Then it says the heatsink is made out of aluminum alloy, uh, aluminum 6063 T1 material and located on top of the CPU. The convection exists on all surfaces with the convection coefficient of 200 watt per meter square Kelvin, ambient temperature 20.85 degrees C, which equivalent to 294 Kelvin. So we are asked to run two scenarios. With scenario one is no heat sinks, and meaning that the CPU is supposed to only cool off with convection to air across all other CPU surfaces, meaning that except the surface that he generates, the other surfaces is open to air. Scenario two is when you are putting a heatsink on top of the CPU and the convection is uh, on all other surfaces, meaning that CPU plus heatsink. And we are going to report to see, temperature plots and temperature chart versus maximum and minimum temperature point. And eventually we are going to compare these two scenario results together in order to evaluate that what was the performance of heatsinks and if the heatsinks provide any better cooling. Um, so let's look at the file that we have. So both files are within the assembly, which is provided. Let's start simulation. So going to simulation and I'll put it a case for CPU, call it, and make sure static is selected. So here I can run like, for example, let's say I could call CPU and call it no heatsink. That's the name of the simulation case. So if I look at the part, I have to first define the materials. So CPU is made out of the copper. Right click, apply material, maybe, yeah, copper is here. So I'll select copper. And heatsinks is aluminum 6063, which is not in this favorite material. We're gonna go over there and select aluminum alloy 6063 T1. Double check. Yes. Apply, close. So material has been applied to both, and then I guess maybe, yeah, I think I have to apply a simulation based on a okay, so I guess this is not the simulation. We have to select the thermal, not static. Yeah, it's a thermal, and then call CPU no heat. So, yeah, it's not a static. It's more like a thermal analysis. Okay. So one more time, apply material, copper, and heatsink 6063. Okay, so now we have to define a thermal load, which we know that. So in the first case, I defined for both parts, but I don't want it to have heat sinks in the first part. So I would right click and I have to exclude this from analysis because in the first analysis case that I have, I don't have a heat sink. So it's only CPU. Now for thermal load, right click and I have to define a heat power. And the heat power as it says, would be this phase, and it would be 40 watts, right? Uh, 40 watts. So that would be 40 watts. You should not select reverse selection, because if you do that, essentially instead of dissipating, it's absorbing uh, heat power. So yeah. So this is dissipating the power. Now we have to define a convection at this point. Uh, so if I go to right click the thermal load, you will see that I can define a convection. And in order to see the convection, I have to select all exposed faces. But as it says in the problem, on all other CPU surfaces, it means that obviously the part that are generating the heat power is not going to be there. So I'm going to deselect this. So I have to select the top because it sees, you see that the top surface is not selected. So we have selected on all surfaces that we have except the surface that it generates heat. So according to problem, this is 200 watt per millimeter per meter Kelvin, and ambient temperature is 294 Kelvin. Okay, so we define heat power and convection, and that's all we need really. Now we're going to create a mesh for the problem that we have. You can stick to default, or you can find it to you. I go with the default. Then let's run the study. And temperature is better to be in Celsius because Kelvin is very difficult, and actually it's required that the temperature chart be in Celsius. So we're gonna go to the definition, the temperature Celsius. Actually, I can, let's do that floating number so we can see what is the number would be for floating. Does it require maximum or minimum? Yeah, maximum minimum. So maximum minimum, hit OK. You'll see that it's gonna get really hot, and look at the hottest point in the back of the CPU, right in the center of that, with 93 degrees. But essentially on all other, like a very close to the corner of the CPU, is the coolest point further away from the surface, which is the 92 degrees. Not too much uh, essential difference, but yeah, it's that's a temperature that essentially the CPU gets without a heatsink. And we are going to do the same study. So I would right click on this one and create a like a copy this study. And the newest study that, so I'm copying from the CPU no heatsink, and the newest study would be CPU with heatsink. Okay, so even I can include mesh to just save time on the previous day. Now in this case, I have to bring back heatsink. So right click and include that in analysis, but I have to tweak a few things. Essentially, heat power is the same. Well, bring mesh doesn't help because we added in part of mesh anyway. Heat power is the same, but convection is going to be different. So going to heat definition, and essentially you can right click and clear selection because you have to select wide few like all exposed faces. It's gonna select every face that exists. The only thing that you have to deselect is in the back of the CPU. The rest of that is good. And the reason that back of CPU is not gonna, because it's probably stick to the PCB, and that's why we don't want to include the heat dissipating surface to the convection. But every face is exposed, it's going to be to the same temperature and the convection rate. So we are going to create mesh again. Select in the center to do the mesh. So we should expect naturally that since we put a heatsink and that add the contact surface with surrounding air, the temperature should be less than that 93 degrees that we had from previous result. But the question is how much is that? So okay, now we have our mesh. I think now we can run this study. Okay, I'll pause the video and resume it after we get the result. Okay, it may take time to have this result, but you will see that we have the result. Let's do the same approach for temperature. I will change it to Celsius, and then I put min and max with the floating display. So now you will see that the result is much better. Let's just take the thermal load right now. So you will see that now back instead of 93 degrees is 28 degrees. And furthest point of this heatsink has only 24 degrees. So you will see that how heatsinks significantly improve the cooling performance of our setup. So yeah, uh, I hope you learned something about this thermal analysis using static simulation package. Thank you.